to Tungal online classes. Today we are going to discuss about the concept of self-induction. Self-induction. In the last lecture we discussed the concept of induction and mutual induction. Mutual induction. So what is the mutual induction? In the case of the mutual induction, if a main current is passing through the primary coil, and this primary coil will be causes the change in magnetic flux. This primary coil is what? Causes what? Change in magnetic flux, and the flux is linked with the secondary coil. As a result, the induced EMF is produced in the secondary coil. That what we discussed in the case of the mutual induction. So once again, in the case of the mutual induction, the primary current or the source current is passing through one coil, and the external magnetic flux will be created in the first coil, and the induced EMF will be developed in the another coil. Such a type of induction we are calling as what? Mutual induction. So what is the meaning of the self-induction? In the self-induction, the primary current as well as change in external magnetic flux as well as the induced EMF, all these things are belongs to a single coil. Once again, in the case of the self-induction, the primary current is passing in a given coil. This primary current will be causes the change in external magnetic flux. And due to this change in external magnetic flux, the induced EMF is also produced within the same coil. Such a type of phenomena we are calling as what? Self-induction. So what point we have to understood, and what is the difference between the mutual induction and self-induction means? In the case of the mutual induction, you are taking the two different coils, primary coil as well as secondary coil. In the primary coil, main current will be there. In the secondary coil, induced EMF will be existing. But in the case of the self-induction, only one coil will be there. In that coil only main current will be flowing. As a result, that is producing the change in external magnetic flux. As a result, that is inducing the induced EMF in the same coil. Such a type of phenomena we are calling as a what? Self-induction. So how can we define the self-induction means? The definition: the phenomena due to which the induced EMF or induced current is produced in a coil due to the change in magnetic flux, which is produced by the same coil, Such a phenomena is calling as self-induction. So what is the definition of the self-induction here? It is the phenomena due to which induced EMF or induced current is produced in a coil, and which is due to the change in a magnetic flux, which is due to what? change in a magnetic flux that was produced by the same coil, such type of phenomena we are calling as a what? Self-induction. So how it is producing within the same coil means, to explain the self-induction we consider an inductor coil. So what is this? We consider what? Inductor coil we consider. This inductor coil will be connected to a battery. Along with the battery, a key will be connected in series with the battery as shown in the figure. So the inductor coil will be represented with the symbol of a capital L, inductance. So here, to explain the concept of the self-induction, here we consider only one coil. But in the case of the mutual induction, you consider the two different coils. One of the coil you named as the primary coil, and the other coil will be named as a what? Secondary coil. But in the case of the self-induction, we consider only one of the solenoid, or that is nothing but inductor coil will be considered, that is connected to the power supply or nothing but a battery, and which is also connected to the plug key. So that should be connected in series with the given battery. Now, whenever the key will be closed, so what happens? Current is passing through the given circuit. Whenever this plug key will be closed, current will be passing through the given circuit. Whenever the constant current will be passing through the given coil, so constant flux is linked with this inductor coil. So whenever the constant amount of current will be passing through the coil, the flux linked with the inductor is also what? Constant. The flux which is linked with the given conductor is also what? Constant. Whenever the flux will be constant, change in flux is equal to 0. As a result, induced EMF also is equal to 0. When you consider whatever the current that is produced within the given circuit, if that current magnitude will be constant, that is producing the constant magnetic flux. Constant magnetic flux. Whenever the flux will be constant, there is no change in magnetic flux. According to the principle of the electromagnetic induction, whenever there is no change in magnetic flux, induced EMF is equal to what? 0. So, to existing that, or to producing the induced EMF, what we need means, we need the change in a magnetic flux. How the change in magnetic flux will be existing means, so we are assuming that the current value will be increasing. Whenever the current passing through the given circuit will be increases, the flux which is linked with the flux linked with the inductor coil, is also to be increases. Whenever the current value will be increases, the amount of the magnetic flux which is linked with the given conductor coil will be increases. So whenever the flux will be changes, change in flux will be existed. As a result, induced EMF is also produced. Whenever there is a change in magnetic flux which is linked with the given inductor coil will be there. As a result, induced EMF was produced within the same coil. Here, whatever the induced EMF produced within the given inductor coil is also be calling as back EMF. Here important, what is the definition of the back EMF means? What is the definition of the back EMF? Means whenever we are increasing the current, which is passing through the given circuit, as a result the magnetic flux linked with the inductor coil will be changes. Magnetic flux linked with the given inductor coil will be changes. As a result, induced EMF was produced within the given inductor coil. Such a type of EMF we are taking as a what? Back EMF. Why we are calling this EMF as a back EMF means? What is the Lenz's law statement? According to the Lenz's law statement, the polarity of the induced EMF is always such that it will be opposes the change in external magnetic flux. Here, the external magnetic flux will be produced by whom? The current value. So here, if the induced EMF is opposes the change in external magnetic flux, means it is also opposes the source of the magnetic flux. That means whatever the either induced EMF or back EMF which is produced within the given conductor coil, will opposes the either increasing in the current or decreasing in the current. That is the main role of the back EMF. Once again, what is the main role of the back EMF? Means the back EMF is always opposes either increase in the current or decrease in the current which is passing through the given inductor coil. So that the back EMF is always opposes the either growth of the current or decay of the current. So what is the main role of this back EMF? Means 2 marks question, very important. Define the back EMF and what is the use or what is the role of the back EMF? Means back EMF is always opposes the either growth of the current or decay of the current which is passing through the inductor coil. So this is what about self-induction. Once again, see what is the major difference between the mutual induction and self-induction? Means in the case of the mutual induction, you took the 2 different coils. Due to the flow of the electrical current in the primary coil, you identified the induced EMF in the secondary coil. But in the case of the self-induction, you taken only one of the coil. Through this coil, current will be flowing. As a result, through this coil, magnetic flux will be changes. As a result, the induced EMF is also produced within the same inductor coil. Such a type of phenomena we are calling as a what? Self-induction. So here, whatever the EMF is produced in the case of the inductor coil, that EMF will be calling as a what? Back EMF. Why we are calling this a back EMF? Means the back EMF is always acting in opposite direction to the either increase in current or decrease in current. So that's why we are calling that induced EMF will be as back EMF. This is the introduction part about self-induction. Next concept is what? Coefficient of self-induction. The similar type of concept we discussed in the mutual induction. There you derive the coefficient of mutual induction. There you wrote one formula. Phi is directly proportional to the I. What is the phi denotes? Phi is denoting the induced flux. Phi is denoting what? Induced flux. The induced flux which is induced in the secondary coil is directly proportional to the current flowing through the primary coil. That's what you wrote in the case of the mutual induction. In the case of what? Mutual induction. So once again, in the case of the mutual induction, what you wrote that the amount of the induced flux which is linked with the secondary coil is directly proportional to the amount of the current which is flowing through the primary coil. But in the case of the self-induction, there is no primary coil as well as there is no secondary coil. Only one coil we have. In that coil only main current will be flowing as well as induced flux also linked with the same coil. So that in the case of the for the self-induction, so what we will write? For the self-induction, the amount of the flux which is linked with the given coil, is directly proportional to the amount of the electric current passing through the same coil. The amount of the electric current which is passing through the same coil. Once again, so for the self-induction only we have a single coil. That's why I am writing that the amount of the flux which is linked with the given coil, is directly proportional to the amount of the electrical current which is passing through the same coil. So to remove the proportionality, we have to introduce one constant. In the case of the self-induction, the proportionality constant is indicated with capital L. In the case of the self-induction, the proportionality constant will be indicating with what? Capital L, where capital L is calling as coefficient of self-induction. So what is the capital L here? The capital L will be denoting what? Coefficient of self-induction. Now, how can we define the coefficient of self-induction? See here, from the above equation, can I write L is equal to phi by I? L is equal to what? Phi by I. So L is equal to phi by I. What is the phi? The amount of the flux linked with the given coil, and I is denoting what? The amount of the electrical current which is passing through the either given circuit or given coil. So the coefficient of self-induction is defined as it is nothing but the amount of the flux which is linked with the given coil, when a unit current is flowing through it, will be flowing through it. See the definition of the L. It is equivalent to the magnetic flux linked with the given solenoid, given inductor coil, when a unit current flows through it. So this is the definition of coefficient of self-induction. What is the definition? Once again, see, it is equivalent to the magnetic flux. Which is linked with the given solenoid or given inductor coil when a unit current will be flowing through that given coil. So that is calling as what? Coefficient of self-induction. Now, whenever there is a change in magnetic flux will be there, induced EMF is also produced within the given coil. That induced EMF we are calling as the back EMF. So from the Faraday's law of electromagnetism, so what we will write? E is equal to minus d phi by dt. So what is the basic equation we know from the Faraday law of electromagnetic induction means E is equal to what? Minus d phi by dt. E is equal to what? Minus d phi by dt. So E is equal to minus d by dt of phi is equal to what is the value? Phi is equal to L into I. Phi is equal to what? L into I. So substitute L into I here. So E is equal to minus L into di by dt. E is equal to what? Minus L into di by dt. So the above equation is giving what? The expression for the back EMF. So the above equation denotes the back EMF produced within the inductor coil. So what is the above equation is giving what? The above equation giving the amount of the back EMF that was produced within the given inductor coil. So this is about coefficient of self-induction and the expression for the back EMF. Once again, what is the SI unit of coefficient of self-induction? SI unit of coefficient of self-induction is similar to the coefficient of mutual induction. Its SI unit is also what remains same, that is nothing but Henry, and the dimensional formula will be given by ml square t power minus 2 a power minus 2. The dimensional formula of coefficient of self-induction is the what? The dimensional formula of the coefficient of self-induction is ml square t power minus 2 a power minus 2. So this is about what? Self-induction and coefficient of self-induction and the expression for the back EMF. Next concept is self-induction of a solenoid. Very important question. So here, how can we derive the coefficient of self-induction for the given solenoid? So going to the basics once again. So here, what we consider here? Here we consider a long solenoid whose length will be given by small l. So length of the solenoid is a what? Small l. And here we are assuming that the solenoid is consisting of a capital N number of turns. The solenoid is consisting of what? Capital N number of turns. Therefore, the number of turns will be taken as a capital N. Number of turns is equal to what? Capital N. So if you know the total number of turns and the length of the solenoid, we define one more quantity, small n. Small n is indicating what? The total number of turns present per unit length. So small n is denoting what? Total number of turns present per unit length. So once again, what we consider here? Solenoid will be considered. So the length of the given solenoid will be taken as a small n, small l, and total number of turns is equal to what? Capital N. From this I define the quantity small n is equal to capital N by L. Now, if we assume I amount of current is flowing through the solenoid. So whenever some current is flowing through the solenoid, at the center of the solenoid, already we have the expression for the magnetic field intensity. So the magnetic field intensity at the center of the solenoid is so what is the basic formula? B is equal to mu naught Ni. B is equal to what we know the formula? Mu naught small n into I, where small n is indicating what? Total number of turns present per unit length. Now, whenever a current will be flowing through the given solenoid. Whenever a current will be flowing through the given solenoid, as a result, magnetic field will be existing. Magnetic field will be existing at the center of the solenoid. Now, I am assuming that if the current value I will be changes, if the current I value will be changes, if a current value will be is equal to constant, the magnetic field intensity will be constant. As a result, the flux associated with each turn of the solenoid is also to be constant. Once again, whenever you are assuming that the current which is passing through the solenoid is to be a constant value, that is producing the constant magnetic field, that is producing the constant magnetic flux, but in the case of the EMF what we are discussing, whenever the flux will be changes, induced EMF will be produced. So that's what I am assuming here. If the current passing through the given solenoid will be changes, as a result, magnetic field intensity, the magnetic field intensity inside the solenoid is also changes. Whenever the magnetic field intensity will be changes, the flux linked with each turn will be given by phi is equal to B into A. So, whenever the magnetic field will be changes, so I calculate that whatever the flux will be linked with the each number of turns. So, for a single turn, the flux value is equal to what? B into A. Here you assume the solenoid will be consisting of capital N number of turns. Therefore, total flux phi total is equal to what we will write? BAN. So, whenever the current value will be changes, magnetic field is also changes. Whenever the magnetic field is also changes, whatever the total flux linked with the given solenoid is also changes. Total flux will be also what? Changes. Whenever the total flux will be changes, as a result, induced EMF will be existed. So, here what we are going to derive here, we are going to derive the expression for the coefficient of self-induction for the given solenoid. So, already we know that from the principle of self-induction, we know that total flux is equal to L into I. That's what we wrote earlier. So, according to the principle of the self-induction, the total magnetic flux which is passing through the given coil, will be is equal to L into I. So, what is the total magnetic flux value here? BAN. So, B into A into N is equal to L into I. BAN is equal to what? L into I. So, substitute the value of B. B is equal to mu naught small n into I into A into N is equal to Li. So, here I will be getting cancelled. So, here mu naught small n means what? Capital N by L. Mu naught small n is equal to what? Capital N by L. Again here one more n will be there into A is equal to capital L. Is equal to what? Capital L. The coefficient of self-induction. The coefficient of self-induction of the solenoid becomes to what? L is equal to mu naught n square A by L. Very important formula. So, what is the expression for? The coefficient of self-induction of the given solenoid is equal to what? L is equal to mu naught n square A by L. L is equal to what? Mu naught n square A by L. So one more theory bit also they are asking, the coefficient of self-induction is directly proportional to, the coefficient of self-induction is what? Directly proportional to square of the number of terms. The coefficient of self-induction is what? Always directly proportional to what? Square of the number of the terms. So this is the expression for coefficient of self-induction. Now here the coefficient of self-induction will be depends upon, the coefficient of self-induction will be depends upon some of the factors. First one, mu naught. What is the mu naught? Permeability of the given medium, permeability of the given medium. So that the L will be depends upon medium present inside the solenoid. So L is depends upon what factor? The L will be depends upon the medium which was present within the solenoid. If a vacuum will be there, less number of lines of force are passing. If a medium, magnetic material medium will be there, more number of lines of forces will be passing. So that the L will be depends upon what factor? The first one is what? The medium which was present within the given solenoid. And the second one is what? The number of turns present in the solenoid. The number of turns present within the solenoid. And the third one is what? Area of cross section. Third one is what? Area of cross section. And the fourth one is what? The length of the given solenoid also. Length of the given solenoid also. So here the coefficient of self-induction is depends upon what factors? Means first one, it is depends upon the medium surrounded by the solenoid, and second one is what? Number of turns present within the solenoid. Third one is what? Area of cross section, and also length of the given solenoid. On these factors, the coefficient of self-induction will be depends. So this is about what? Self-induction of a solenoid. Self-induction of a solenoid. Next topic is the energy stored in an inductor coil. The energy stored in the inductor coil. See here, already we told in the case of the self-induction, whenever a current will be passing through the given conductor coil or a solenoid, induced EMF will be existed. That induced EMF we are calling as a back EMF. So in the case of the given solenoid, due to the change in a current, as a result the magnetic flux which is associated with the given solenoid is also changes. As a result, the induced EMF will be produced. Within the given solenoid. Such a type of induced EMF we are calling as back EMF. Already I told what is the role of the back EMF. The back EMF is always opposes the either growth of the current or decay of the current. So what is the role of the back EMF? The back EMF is always opposes the growth of the electrical current which is passing through the given circuit. So here I want to send a constant amount of the current in the given circuit. What I want to do? I want to send a constant current in the given circuit. But due to the induced EMF or a back EMF which was produced across the inductor coil, this inductor coil will be opposing the incoming current. To overcome that opposition and also to maintain the constant current in the given circuit, to overcome the opposition which was offered by the back EMF as well as to maintain the constant current in the given circuit, we have to did some external work. So what is the need of this work? So we did some external work we did some external work to overcome the opposition offered by the back EMF as well as to maintain the constant current in the given circuit. So what is the need of this external work? Means the need of the external work is to overcome the opposition which is offered by the back EMF, as well as by overcoming that opposition to maintain the constant current. We have to did some external work done. So this external work done, is stored in the form of a potential energy inside the inductor coil. So whatever the work we are doing to overcome the opposition offered by the back EMF as well as to maintain the constant electrical current in the given circuit, that will be stored in the form of a potential energy in the case of the given inductor coil. So that's what we are going to derive the expression for energy stored in the inductor coil. So now we are going to derive the expression. So this is the derivation part. So in this derivation part, here we consider a source of EMF calling as the battery, whose potential difference or EMF will be given by capital E, and the back EMF which is produced across the inductor coil is equal to what? E is equal to minus L into di by dt. di by dt. So whatever the terms are present within the circuit, now here I am writing that the potential difference across the battery is equal to what? Capital E. Across the battery is equal to what? Capital E, and back EMF across the inductor coil. So E is equal to minus L into di by dt. E is equal to what? Minus L into di by dt. So these are the potentials which are present. Within the given circuit. Now, what is the Kirchhoff's second law? According to the Kirchhoff's second law, the algebraic sum of the potential difference as well as EMFs which are present within the given coil, will be is equal to 0. So I will apply the Kirchhoff's second law for the given closed circuit. Let it be ABCD. So I consider the closed loop ABCDA. So here the direction of the current will be flowing in this direction. So here, what is the EMF present here? The EMF present value is equal to what? Minus L into di by dt. This is the EMF across the given inductor coil, and whenever you are coming to this portion, you are moving from the negative terminal to the positive terminal. Whenever you are moving from negative terminal to the positive terminal or low potential to the high potential region, potential drop will be taken as a positive. So if we apply the Kirchhoff's second law, what we got here? Minus L into di by dt plus E is equal to 0. From this I will write E is equal to E is equal to what? L into di by dt. E is equal to what? L into di by dt. What is the capital E? Potential difference. What is the capital E? Potential difference. Potential difference E is equal to what you got? Di by dt. Now, again, what is the role of the back EMF? It will be opposes the further increasing in the current. It will opposes the further increasing current. So I want to send a small amount of the electrical current. I want to send the small amount of the electrical current. For that we have to do some external work done. So I know the basic formula for the work done. So work done, W is equal to what? We know the basic formula. Work done is equal to what? W is equal to V into Q. So here I want to send dq amount of charge. I want to send dq amount of a charge in a time of dt seconds. So the current is nothing but the rate of change of the electrical charge. So here I want to send a small amount of the charge dq in a time of dt seconds. So here I want to send a small amount of the electrical current. I want to send the small amount of the electrical current, that is nothing but dq by dt. So here I is equal to what? dq by dt. I is equal to what? dq by dt. So the total work done is equal to what? W is equal to V into Q. So the rate of work done is required to send dq amount of charge in a time interval of dt seconds is. So to send the total amount of the charge q, what is the work needed? W is equal to V into Q. But so I want to calculate the rate of work done. So the rate of work done is equal to dw by dt is equal to V into dq by dt. V into what? dq by dt. So here dw by dt is equal to what you got? V into dq by dt. Here V is indicating what? Potential difference applied in the circuit. V is indicating what? Potential difference applied in the circuit. So here in the place of V I will write capital E. In the place of V I will write capital E, and dq by dt is nothing but electrical current. dq by dt is nothing but electrical current. So here dw by dt. So dw by dt is equal to E value. So what is the E value from the equation number 3? E value is equal to L into di by dt. Once again I will be there. Here I will be there. So here this dt value will be getting cancelled. Therefore you got dw is equal to Lidi. So here dw is denoting what? dw is the work done to send a small amount of the electrical charge, in a time of dt seconds. So to get the total work done, so we have to do the integration. Total work done, W is equal to integral dw. So substitute these values here. Integral Lidi. So L is the constant. Integral Idi. So integral x dx is equal to what? X square by 2. Therefore this value is equal to L into I square by 2. Therefore the final expression is equal to half L I square. The final expression is equal to what? Half L I square. So this is the expression for total work done is required, or this work done will be stored in the form of a potential energy. potential energy. Hence, the energy stored in the inductor coil will be given by U is equal to half Li square. What is the required equation? U is equal to what? Half Li square. This is about energy stored in the inductor coil. Thank you.